So you keep the evidence. Ah.
Okay, good afternoon, everybody. So today I have a pleasure to introduce ANDRZEJ DRAGAN. He's well known for work in so-called relativistic quantum information. That's where we also met each other at some of the conferences of this association. He started to receive his kind of awards already as a master student. I realized in 2001 was the best master thesis in Poland. In 2005, he received his PhD. Please correct me if I made something wrong, with Konrad Panaszek, working on quantum information, more conventional quantum information. And then he moved for several posts at Imperial College and also University of Nottingham. I think that is the time when you really then went into the relativistic quantum information with all kinds of problems, for example, extracting entanglement from vacuum states and quantum fields and similar things. He is now a professor at the University of Warsaw and also visiting professor at Singapore, University of Singapore. One effect bears his name. It's the ANDRZEJ effect, the Dragan effect.
Yeah, but not in physics.
But not in physics. It's an effect in photography. I mean, if you Google, you will immediately see what it is. So he's very successful as a photographer and also as a movie maker. I read this, but I don't remember, several awards and different festivals, film festivals. And recently, what I've been following his YouTube lectures on unusually special relativity, in which you have somewhat alternative derivations of some of the results in special relativity. I think it's very enlightening and very amusing, and the videos are somewhat in style of his movies. And so, okay, that's where I finish. Today he will present something what is somewhat controversial. It's a work with Arthur Eckert about derivation of some elements of quantum theory out of special relativity.
Yeah. Thank you very much. It's a pleasure. It's, as I said, it's really my first time in Vienna, properly being here, other than just traveling by. So I would like to have a look at the city. But this talk will be really about special relativity, and I still hope to surprise you with some of the observations. And I'm sure you recognize this figure. Does anyone know where is it from? Yeah. Hmm? No, you don't recognize it. It's from Feynman's lectures on physics, the third volume, where he introduces quantum theory in a very unusual way, and he claims that he can actually understand all the theory based on just very elementary postulates. And he neglects Schrödinger equation. He postpones it until like page 200 or something. He discusses other stuff that he finds to be more relevant. And he thinks that everything about quantum theory can be understood based on this double-slit experiment, where you can look at the experiment, the outcomes, and conclude about three fundamental properties of nature. The first one is that outcomes of single measurements are fundamentally unpredictable. They're indeterministic. You cannot predict them. There is nothing underlining the outcomes. We call it that there is no local there is no local theory of hidden parameters that could explain those experiments. Second of all, he says that the second postulate, kind of unexplainable postulate, is that if a system can evolve along more than one trajectory, then it's not going to choose, it's going to use all the trajectories at the same time. And you call that superpositions. And the third thing is that in order to describe a motion like that, you need to use complex numbers. And in particular, if you do not observe the system as it evolves, you will have to attribute a complex number to each of the scenario, and then you have to sum up all the complex numbers, take a modulus square, and that's how you get probability of a given outcome. And if you do observe the system, it will behave randomly, unpredictably, and you won't be able to predict the outcome of a single measurement. And essentially, he says that this is all you need to know about quantum theory. Everything else is just details. And then he concludes that with the following quote. One might still ask, how does it work? What is the machinery behind the law? No one has found any machinery behind the law. No one can explain any more than we have just explained. No one will give you any deeper representation of the situation. We have no ideas about a more basic mechanism from which these results can be deduced. And the talk today is essentially, can be summarized by saying, challenge accepted. So in 2020, me and Arthur Eckert, who I guess needs no introduction, wrote a paper where we claim that, in fact, you can explain these things with something more fundamental and more basic. And to the surprise of everyone, this thing turns out to be special relativity. So we claim that you can derive these things that I just described using very elementary consideration with just special relativity, but somehow treated in an unorthodox way. So what we have found is that it is known that if you introduce some sort of superluminal phenomenon in special relativity, you have problems with causality. You get some sort of paradoxes, causality is disturbed, and that's why people reject those extra possible superluminal objects as unphysical. And what we have done is we have investigated how exactly would reality look like if you treat those superluminal phenomena seriously, and what you get is indeed you get problems with causality, but not as a paradox of any kind, but as in exactly the same way that we already know from quantum theory. So causality in quantum theory is already disturbed. You can repeat the same experiment several times, get different outcomes, and what we found is that this is exactly the type of thing you get when you consider special relativity, including superluminal objects. And you may think that Einstein is rolling in his grave because of his famous dislike of quantum theory. He kept repeating that God does not play dice, but nothing could be further from the truth, apparently. Einstein is apparently alive and well, and he runs a Twitter account where he tweeted about this work, so apparently he's not rolling in his grave anymore. So let me tell you about this from the very beginning, and I would like to start with a very quick derivation of Lorentz transformations, but somehow in an unorthodox way. So what I want to do is I want to assume principle of relativity in a way it was formulated by Galileo 400 years ago, and I am not going to assume the constancy of the speed of light, and you still can derive special relativity without that extra assumption. So this is how it follows. So first of all, you notice that the transformation laws between two inertial observers, one is resting observer, the other is moving with velocity v along the x-axis, should be linear, because only linear transformations do not discriminate any point in space-time. And the coefficients that we do not know, a and b, should only depend on the relative velocity, let me call it v. And if you have the first equation, you can immediately write the second equation because of the principle of relativity, because if the prime frame is moving with velocity v relative to the unprimed frame, then the unprimed frame is moving with velocity minus v relative to the prime. That's all. And now your goal is to determine those coefficients a and b. So the easiest way to do it is to consider the origin of the moving frame of reference, x prime equal to 0. And in the resting frame, it should be described by the equation x equals v times t. It's just moving with constant velocity. And if you take those two and plug it in the first equation, you get a relation between b and a. You could plug it back to the first equation, do some simple transformation, and you get this. And this is the most general form of transformations that could be in agreement with Galilean principle of relativity. What you don't know is the coefficient a, and your goal is to determine the coefficient a. The simplest scenario would be that a is equal to 1, and then you get this is 0, this is simply x minus v times t, and you get Galilean transformation. But in general, a can be something else than a, than 1, and let us determine what it is. And the only thing we can say right now about a is that it has to be either a symmetric or antisymmetric function of velocity. Anything else doesn't make much sense. And that is because if you consider the moving frame to have an x-axis flipped for some reason, then such an operation should only introduce some sign change in the transformations. And since flipping x involves changing the sign of velocity, then if you only want the sign flips to appear, then a has to be either symmetric or antisymmetric. And the last step to derive Lorentz transformations is to consider not two but three inertial observers. The first one is resting. The second one, the primed one, is moving with velocity v1 relative to the resting one. And the double primed is moving with velocity v2 relative to the primed frame of reference. And what we want to do is to compose the transformation so that you get a transformation between this guy and this guy. So you have to compose those formulas twice, and this is the outcome. And it depends on both velocities v1 and v2. And now I would like to notice something. So if I wanted to find the velocity, the relative velocity between the double primed observer and the unprimed observer, I can look at this equation that I already had before and notice that velocity is simply the ratio between the coefficient in front of t and the coefficient in front of x. If I divide the coefficient in front of t by what stands in front of x, I get velocity up to the sign. And applying this to my formula, I get this. This is the relative velocity between the double prime observer and the unprimed one. And again, if a was equal to 1, this is simply the addition of velocities. And in general, something more complicated. And the crucial observation is right now. You can notice that if you compute the velocity between the resting guy and the double primed guy, we could get the same result by computing it in the opposite order. So first start at the double prime observer, then transform yourself to the primed observer, and then transform back to the resting observer, which means that you have to reverse the velocities. Instead of v1 and v2, you have to use the velocities minus v2 and minus v1, which means that you can just swap the velocities, and the outcome should be the same. This is essentially what I said. And now you can compare those formulas. And what you get is that since numerators are the same, unity is the same, this product is the same, all that differs is the fraction here. So those fractions have to be the same. But now you can see that the first fraction only depends on v1, and the second fraction only depends on v2. And that simply means that this whole thing has to be equal to some constant, because it's some function of argument, and for two arbitrary arguments at the same value, it must be a constant. And we can call that constant k, whatever. It has the dimension of inverse squared velocity, And we don't know the value of that constant. But there must be some constant, historically it's denoted by 1 over c squared, that exists and characterizes this formula. And now we are already done, because if you consider a symmetric function, you can solve that equation and get this. And as a result, you conclude that, based on these formulas, you can say that speed of light is preserved. This constant c that appeared in formulas, you can call it speed of light, and it's the same in all frames of reference. You don't have to assume it, it's just a consequence of the Galilean principle of relativity. So essentially, everything I have done so far could have been done by Galileo already 400 years ago. But there is a second possibility. A could be antisymmetric function, which is also a mathematical possibility, and that leads to the following set of outcomes, which is also a mathematical possibility, as I said. And the first solutions only work for velocities smaller than c. These formulas only work for velocities larger than c. And if you check all the conditions, they satisfy the constant speed of light, they satisfy all the requirements, so really any derivation of Lorentz transformation should always give you these formulas as well as an alternative solution. If it doesn't, then probably you have overlooked something, or you have used some additional assumption that rule out these extra solutions. So again, if you think about Galilean principle of relativity that says that all inertial observers are the same, then there is no reason, just based on this principle, to rule out any of these outcomes. You can only use an additional postulate to say this is unphysical, we don't like it, and that's why we only consider the first family of observers. But mathematically, it's still possible to consider superluminal observers, and formulas are well defined, there are no complex numbers whatsoever, and so on. And by the way, this is the first solutions are the hyperbolic rotations of spacetime, where you have the axis tilt by the angle that is smaller than 45 degrees. These transformations are also hyperbolic rotations, but by the angle that is larger than 45 degrees. And in the extreme case scenario, when the observer is moving infinitely fast, this transformation will simply exchange time and space. So that is the mathematical possibility. And as I said, usually one disregards this as unphysical, and what we have done in the paper is essentially looking at the consequences of these extra solutions, and we wanted to investigate what happens if you take them seriously. Are there any questions or comments? By the way, interrupt me anytime you want. Yes.
So the first set of equations, they just give you, they are both a geometric interpretation as Lorentz transformations, preserving metric. Is there a similar space-time picture also for the second kind of transformations?
So,
is there a metric that is preserved?
So the speed of light is preserved, first of all. So if something moves the speed of light in one frame, it will also move in the speed of light in the other frame. In general, the space-time interval would change the sign. So what was space-like will become time-like, and vice versa. So it does not preserve the interval, but it changes the sign of the interval. At least in 1+1 dimensions. In 1+3 dimensions, it's more complicated, and I don't think maybe I'll have time to talk about it, but it's even more interesting there. Any other questions or comments? Okay, so let us try to investigate what is the consequence of using superluminal objects in special relativity. So the way you teach students that it's not allowed to talk about superluminal signals is this. Suppose that there are two guys that exchange a superluminal signal. Suppose that it's possible. And then you can show that there always exists another inertial frame of reference that is moving with subluminal velocity, for which the order of these events is reversed. So in the resting frame, you have A and then B, and in the other frame, you have B and then A. And that's a problem, because if this was a signal that sends some information or has some causation, then in the first frame of reference, A caused B, and in the other frame of reference, the cause would happen before, would happen after the result, which is an absurd conclusion, and that's why people say it doesn't make sense. But I would like to have a look at this slightly more carefully, and I would like to use the familiar language of quantum information, where you talk about things using the so-called local hidden variable theory. So if you say something about this event here, that the signal has been sent, what you really mean is two things. First of all, you say that you have a carrier of superluminal objects, some bullet that you could shoot with a pistol and pull the trigger and the bullet pops out and the bullet moves with superluminal speed. But second of all, you have to make the bullet pop out. You have to have some sort of causation. You have to be able to trigger the bullet. So there must be some parameter here that determines the exact moment at which the signal has been sent, if this is to be a signal. So there must be some mechanism, some local hidden variable or visible mechanism that you can control and decide at which point you pull the trigger so that the bullet pops out. And obviously, the other guy who is far away is being hit by the bullet, and in his past, there is nothing that would allow him to predict the exact moment at which he's going to be hit. That's why if you look at this trajectory, you won't find any evidence that in 5 seconds you will be hit by a bullet. It's just a trivial observation. And then the same has to happen in this frame of reference. And the question I would like to think about you right now is this. In this frame of reference, it appears that the bullet pops out from D. What caused that emission? Where is the cause of this? If you are just an observer, you would see that there's a guy, and then out of nowhere, there is a bullet popping out of him. Where is the cause of that? So one thing you could say that sounds absurd is that the cause of this is here. But that would be a non-local theory, where you say that reason for this emission happens here in the faraway mechanism. That would be a non-local theory. But if you're looking for a local and deterministic description of this, so somewhere here, you'll not find any. So you see that this emission happens in a way that cannot be described with any local and hidden variable theory. This looks to be completely spontaneous to a local observer. Exactly the way that atom emits a photon. You also cannot predict that exact moment. It happens spontaneously. You cannot predict exactly when the photon will be emitted. So this is exactly like that. And the problem here is that in this frame of reference, this looks to be indeterministic, but in this frame of reference, it's fully deterministic, which is a problem because principle of relativity requires that all frames of reference are the same. And in particular, you could think that those two guys are not really guys, but elementary particles that exchange a superluminal object, superluminal tachyon. And if those particles are identical, then everything that happens here should also happen here. It's perfect symmetric. It's a perfect symmetry. So for that reason, you have to conclude that if you want to impose the Galilean principle of relativity, you need to say that if the process was locally indeterministic here, it has to be locally indeterministic here. Therefore, if you want superluminal signals in your theory, the first conclusion is that they would have to be emitted completely spontaneously, so that there is no local and deterministic theory that can predict the outcome. And that's even more interesting because if the emission is completely spontaneous, then you really cannot use it to signal. You cannot send signals. Because in order to send a signal, you need to be able to control the signal. Otherwise, it's just a random emission. It's not a signal. So there is no information transfer. So the funny thing is that although you have superluminal objects, it's not clear how you want to use those objects to send information. So it's not obvious whether there is paradox at all.
So what does it have to do with randomness? I mean, I could I don't know, put two boxes in different parts of the city, they explode at the same time, and you say, look, there's a connection, this reference frame, this one started this one, or this one started this other one. It's just some interpretation that you're making. You don't need randomness to make sense of this. You have to say, in order to prepare an experiment with this particle goes like this, I have to do something non-local. That's all.
Yeah, I'm not okay. The only thing I'm saying is that if you make local observation, you won't be able to. If you only look at this word line here, you won't be able to predict when it's going to happen. So you have a system, and then there are two particles out of nowhere. And if your task is to say when exactly it's going to happen, you cannot. That's what I say, it's random. I mean, there is no local and deterministic theory. Technically, that's what I'm saying. And randomness is one solution, obviously, but I mean, I don't know what else. Is there anything else? You have a guy, and out of nowhere, a bullet pops out of his body. And you don't know when it's going to happen.
The problem here is that you cannot control it.
You cannot control it.
Exactly, that's the only paradox you have. It's a process that you cannot control.
Yeah.
That's all. Yeah, that's it. You don't need randomness anywhere.
Okay, but
suppose you can predict it. Suppose I can tell you, look, at this time in point A, some bullet is going to come out, and this time in point B, somebody is going to come on the other side. I'm telling you what's going to happen, right? I mean, there's a hidden variable model if you want, right? I mean, but still you cannot control it. You cannot prevent A from producing the bullet or B from getting the bullet.
yes, but you cannot predict it. If that you know that is going to, I mean, it is going to happen at some point. And if I put you at some point on this weird line, you don't know when, you won't be able to say when it's going to happen. So it's like being, I mean, it's completely unpredictable. Maybe the word unpredictable is a better word.
Okay, paradox appears because of that.
But there is no paradox, really. I mean, what is the paradox?
I agree, there's no paradox.
There is no paradox. I'm just saying that if you introduce those objects, they would have to be emitted in an unpredictable way.
Or in a way that you cannot control. You can
Yes.
predict when they're always going to happen. You can predict it, but you cannot control it.
How would you?
Avoid it and you cannot control it.
How do you predict it? How do you predict it?
No,
Based on what?
I'm telling you, God comes from heaven and
Uh-huh.
tells me there's going to be a particle coming from B going to A at this time and this point. This
Well-
is a prediction. That's what the meaning of a prediction.
Yeah, but if, I mean,
No, but you cannot control it. And then you say, no, but I will prevent B from, no, you cannot.
yeah, I mean, but how is it different from the photon emitting from the atom? Is it not exactly the same?
No, I don't think so.
What's the difference?
You cannot predict it. The atom, you cannot predict it. And I'm giving you an example of a theory where you can predict these things, but still you don't get a paradox because you cannot control them.
No, how do you? I mean,
The problem in your case, you could get a paradox. You could get if really A could decide, right? I mean, whether to send the particle.
but they can't. If they,
Exactly, so you cannot control it.
yeah,
That's the way to resolve the paradox. You eliminate the control, but you don't have to eliminate the capacity to make a prediction. I could say, well, I know that at some point I will, or at exactly this point, I'm going to produce a particle.
how? No, you cannot.
Because I have a theory.
No, but that would, if no,
Well, because you can write over the paper
That-
a theory where you have
if
to
you would
say-
be able to predict that it's going to happen,
Yes.
that would prefer this frame of reference from this one,
Why?
because
No, because we can also make a prediction. Can say, look, at this point, I'm going to get a bullet come out of my body.
how based on what? Based on your history.
Based on whatever theory you have. I mean, you're speaking about general theories of physics. I can write you one over the paper that has this thing.
Yes, but I'm saying that this theory cannot rely on what's going to happen in this weird line. Your theory cannot be rooted in any physics in this weird line. This weird line carries no information whatsoever about this event. There is no information. So if your physics, your theory relies on what's happening here, you cannot get the outcome. This is not possible.
Suppose that, okay, the theory actually, suppose that both parts, okay, since close to him there's an object with a counter,
Mm-hmm.
and the counter is really counting, it's a backwards count, and he knows that when it reaches 0, then he's going to get a bullet also his body.
But he cannot. There is no counter because you started with an idea that there are two.
Counter, but the other theory is where there are no counters, right? I mean, you prefer to explain things with randomness. I'm telling you that the problem in this case is the lack of control. Is the capacity or the possibility that one of them could.
It's a fundamental lack of control. How?
Yes, I agree.
So if you cannot control,
I cannot control whether the sun is going to come up, but I can promise you, right? I mean, I can make a prediction. I can tell you that the sun is going to come up at this time, right? I mean,
okay.
I cannot control the sun, right? I mean, but
Yeah.
no one is going to come.
Okay,
to appear.
okay. Suppose I close your eyes and I told you I'm putting you somewhere on this line. How are you
No,
going?
but then you have to give me a theory to do that, to this kind of things.
So I'm saying there is no theory. There is no. If you don't know where you are on this line, you won't be able to predict this event. There is no theory you could get.
No, I'm telling you, it's a theory when it's point of the universe. There is a clock, right? I mean, that tells you whether a bullet is going to come out, and it is counting backwards, right? So when you know that when it reaches 0, and of course you will get a bullet. You can make a prediction.
For that
It's a
theory,
completely artificial theory, okay?
it's like super. What you
Okay,
what you're saying is some sort of super determinism, where you know everything in advance. You know all the universe, all the particles, all the events in advance.
I know everything that relates to this these tachyons that you're putting here.
Uh-huh.
Yeah.
I'm not stopping this because it's very music.
Okay, let me proceed, and I'll be happy to discuss this. Okay, so what I'm claiming is that there is no local and deterministic and relativistic description of this. That's what I'm saying. Okay, so normally you would say there is no local and deterministic description. I'm adding the relativistic because here you could have a relativistic description in one frame, not the other. If you want to have all frames to be equal, then you get this. And that's the first observation, that these objects will, it's not clear how to send signals to these objects, really. So it's not obvious that you get run into paradoxes. I don't think there are any paradoxes with superluminal objects like this. Okay, but what about normal decays like this? Can you predict the moment at which this decay is about to happen? And, well, you know the answer. In reality, if you make an experiment, the answer is no, because all the interactions are quantum, and those types of interactions are random, really. And can you say something about that from these considerations? Well, if you look at this process from the point of view of the superluminal frame of reference, this is like a new step now. Then, for example, if you take the infinitely fast-moving observer that observes this process, which simply involves changing time and space, then this process looks like this in this other frame of reference. So in the superluminal frame of reference, all those particles appear to be tachyons. And for tachyons, we already know that there is no local and deterministic description of this. Which means that if it's to be completely unpredictable in this frame of reference, or uncontrollable, it has to be the same in this frame of reference, provided that you assume the principle of relativity. So this way you can say that if you allow all the observers to describe your process in their frame of reference, and all these observers are equal, then being superluminal is relative. And in fact, in 1 + 1 dimensional spacetime, there is a perfect symmetry between those two families of observers. You could be tachyons in 1 + 1 dimensional spacetime, and you wouldn't even know about it, because it's purely relative. So if there is no local deterministic description of this here, there cannot be description here. So also this process has to be fundamentally random. If you allow, okay, these are the differences I would like to discuss maybe later, but this process appears to be indeterministic. Okay, so this is the first observation, that once you mess up with these superluminal objects, you get some sort of unpredictability of events, which is completely new. In physics, in classical physics, you don't have that. But what about superpositions, like the Feynman described? When you do not observe your system, it will evolve as if it was going along two paths at the same time, provided that you do not make observations.
Maybe I just can comment, like, as far as I understand, like, there is, of course, non-local hidden variable, which is a Bohmian mechanics, but it requires a preferred reference frame.
Yes.
So is it not at the end of the question, is there any non-local hidden variable model which doesn't require preferred reference frame?
I don't think so. So,
and I think he says that it does.
So this is actually what you just said is seen here, because if you do not require relativistic invariance, then as I said before, the reason for this could be here.
Yeah.
So there is a non-local deterministic theory, but there is no.
It's happening on the left-hand side.
Yes.
It's just a
Yes.
information.
So there could be a non-local deterministic theory, as Bohm says. But if you don't want to have any frame of reference preferred, there is no one. Okay, so let us consider the following thought experiment, very simple one. Suppose that we are sitting in the resting frame, kosher subluminal frame of reference, and there is a photon that moves, or a ray of light, say a photon, moves from A, being reflected at a mirror, and then goes back to B. And then I'm going to say something really obvious. If I take two detectors and place two detectors on the path of the photon, one here and the other one here, then if the first detector clicks, absorbing the photon, then the second will not click, because the photon has already been absorbed before. If the second detector clicks, then I'm sure that the first one could not have clicked, because otherwise the photon wouldn't get there. Okay. And now let's have a look at the same scenario, but from the point of view of the observer that moves infinitely fast. You have to apply this transformation, which simply exchanges time and space. You get this. Right. So it appears that in this frame of reference, there is no one photon, but two. The photons are emitted at the mirror. One is moving to the left, the other is moving to the right. But if you make an observation, if you place two detectors, one here and one here, then you know that only one of the detectors can click, never two. So it appears that if you make an observation, you cannot have two clicks. So it's not that you have two photons, really. But if you take away your devices, there are two paths characterizing motion of your photon. It looks like it's following two paths at the same time. In the literal sense, it's not a metaphor. It's just characterized by two paths at the same time. And as soon as you allow those superluminal transformations, these effects are inevitable. They are trivial consequences of relativity. So even if you start with a single path in one frame of reference, you will find another frame of reference in which there are two paths at the same time, not one. So again, effects that look to me like superposition are trivial consequences of taking into account superluminal frames of reference.
Can I ask you something? Like, if I think about the path of the photon, like a really localized photon packet, it goes from A to M to B. But here, it also goes from, like it goes forwards in time, really from M. Like if I may have, you draw the whole trajectory over the whole time. I don't want this.
Yes.
So how it would look like if I have a path on the left?
I don't know. I don't know, because if you have a path, that means you have the preferred direction of time.
Yeah, this one, you have chosen this.
Yes, but you know, all theories, like quantum theory, is insensitive to the arrow of time. So, and also.
No, but I'm just describing in this reference frame the trajectory, and this is allowed. Imagine that many repetitions I measure immediately afterwards, then I measure later on, and then I can reconstruct. Okay, photon was localized.
Mm-hmm.
I don't even need to be too much localized. I just want to know a little bit of the wave function.
I mean, I don't know if the photons are really moving this way. You know, the two-state formalism, what Haronov says about theory.
No, I'm not saying that. I'm not assigning any reality to that. I'm detached. I'm just saying, like, if I have a distribution of the amplitude along this path, how it looks like on the left and right. I'm not saying anything, no ontology. I'm just.
Yes.
Because here I see that they are related to A and B. After all, I can send a signal from A to M, from M to B. I mean, I can construct experiment that will make this signal. How is this on the right-hand side? Because now it seems like M is the source, but I mean, M was definitely something.
I would refrain. I would refrain from any interpretation of this. I would just say that I would avoid going this way. I would only say that things I know about the photon is that it was here at some point. It bounced off the mirror because I can have consequences to that, and it was registered there. That's all I know. I wouldn't venture into saying, oh, it was going this way or that way.
But then these events are really like that. It's on the right-hand side. It's first M and then A.
Yeah. Moreover, what we are doing in this work is just considering what happens if you take into account all observers that you can, including the superluminal ones. And if you do, this is a consequence. And this shows you that thinking about this path as something that has an arrow attached doesn't make sense, because in this frame of reference, this arrow is going like this, and it's an absurd observation. So your picture is possible, but not when you take into account all frames of reference. If you take into account all frames of reference, you have to abandon this idea of an arrow, I would say. So I'm not saying this is what needs to be treated seriously. I'm just saying that if you treat that seriously, that's what you get, and you are familiar with this already. This is what I'm saying is not surprising to any of you, because you know this is what we know from quantum theory for 100 years. So
there's another question that I have. I'm sort of like, what this has to do with quantum mechanics? I mean, why it's not just wave mechanics, classical waves, like theory of relativity. If you say that it can be derived from that.
Mm-hmm.
Like,
yeah.
But why can't we have also classical physics?
Okay, maybe the third point will be more convincing. So, so again, in quantum theory, we know that what is quantum theory? I mean, you not only that you have this picture, a kind of hand-waving picture, but you also have something more concrete, complex numbers and probability amplitudes that you have sum up and take a module square. So the next thing I want to show is that you can get that. So first of all, if you have already that, if you can have two paths, then you can have multiple paths. Because, for example, if in one frame of reference there is a particle that moves from A to alpha, then is scattered and moves along two paths at the same time, then if you look at this from the superluminal frame of reference, you'll see three paths at the same time. And you can iterate it. You can get 4 paths, 5 paths, n paths. This is already possible. So the question that arises is, you end up with motion that is, in principle, that would be possible along such a scenario. How could you characterize this motion? And now I get to the more concrete part where you have some quantitative description. So the question again is how to characterize motion between 2 points if the particle moves along multiple paths. And all you need to assume is, all you can assume is that's relativity. So first of all, what we want from the theory that describes motion like this is that it should be relativistically invariant. This is the most important requirement. It should be the same in all frames of reference. And that means that if you have a single path between A and B, you know what are the relativistic descriptions of a single path. You need to use invariance, and the simplest possible invariant is the proper time along the path. This is the quantity that I call phi, and it's a proper time along a single path. So if I had a single path, this is the relativistic invariant that is the same in all inertial frames of reference. And coincidentally, this happens to be up to a constant equal to this. So if you take energy of the particles and momentum of a particle, plug it in here, you get this. So it appears a little bit like a quantum mechanical phase, which is a relativistic invariant because it's simply a product of for position and for momentum. In fact, Feynman was puzzled by this in his textbooks, in a few of them. He noticed that we have a non-relativistic theory, but we have a relativistic invariant. How is it possible? Right. So if I had a single path, I would characterize it with a phase like this. If I have multiple paths, I would say that my quantity characterizing motion of this sort should be function of phases along all the paths. If I have n paths, 1, 2, 3, 4, n, I should have n phases for each of them, and my invariant function should be function of these phases. And the labeling, how I label those paths doesn't matter. This could be 1, 2, 3, 4, 5, or 1, 2, 3, 4, 5. Therefore, the function that I'm looking at, I'm going to denote it with p, should not depend on the labeling of the phases. So it should be a completely symmetric function. This is some invariant. I don't even know what it is. I'm just considering the most general invariant characterizing such a diagram. I don't even know what it is at this point. And all I want to say is that this invariant should not depend on the choice of labeling. Also, I would like to say that this invariant should not depend on the arrow of time. The theory I'm building should not depend on the direction of time. Therefore, if I flip time, all the signs of the phases will flip, and I want the function to be the same. And now the third kind of assumption about this function will tell me a little bit more about this function, what it is. And this is going to be the last one. I want this to be some sort of probability. And this is the most kind of physical assumption here. So you know that you cannot describe the motion of these particles in a deterministic way. There is this element of unpredictability. So therefore, you want to look at least for some sort of probabilistic description. So I would like to say that this is some sort of probability characterizing this motion. At least this function should have properties of probability. But now the question is, what are the probabilities? Because in different theories, probabilities have different properties. For example, in classical theory, you can add probabilities, and in quantum theory, you cannot add probabilities, right? So what are the right properties of probabilities in your theory? But fortunately, there is one property of probability that is completely general, and it applies to all possible theories. It's really a defining property of probability, and that is that if you have two independent events, then the probability of both of them to happen is a product of probabilities for the first one to happen and the second one to happen. And this is fully general. It happens in classical theory and quantum theory. This is a defining property of probability. So therefore, I would like to consider the special case of motion where all these paths cross at a single point, in which case I can say that the probability of the whole, so to say, is going to be a product of the first part and the second part. That's all. This is the end. This really means that this part, which is this function, times this other part, which is this function, should be the function of the whole, which involves sums of phases, because phase is additive. It's just an integral. So this is the third requirement. And the completely surprising thing is that there are very, very few functions that satisfy all these three conditions. Very few. This is some sort of generalization of Euler's theorem that you may have heard of, one of the theorems. So the outcome of this is this. A special solution of all these conditions has this form, where this unknown function is of the form 1 over a number of paths to an arbitrary power beta times sum of exponential functions with some constant alpha to an arbitrary power gamma times the same sum with negative exponents to the same power gamma. This is a special solution, and the most general solution is product of special solutions. You can show this. Okay, so this is the simplest solution to these three requirements, and it already starts to look familiar. And you show that the most general relativistic probability-like description of this picture, this diagram, has to have this form. So whatever probabilistic theory you have, it must be characterized this way. And there's one more problem. If the number of paths is not finite, because you can iterate, you can have as many paths as you want. If the number of paths is to be infinite, then this invariant will also be infinite, because it's a sum of infinite numbers that are larger than 1. So you will have your probability-like description that is relativistic, but so what, because it's in infinity all the time. It's not interesting. And there is only one way, one choice that you can make to make this finite, or at least to make it that it gives you hope to be finite. Can you guess what it is? What can you do to make this finite, even if the number of paths is infinite? If alpha is a purely imaginary number, then this has a chance to be finite. So as you see that if you assume relativity and like as little as possible about your theory that it has to be probabilistic, you don't have much choice.
Can you please repeat where on this slide relativity?
Yeah, here. That this is a relativistic invariant.
Yes. Or it's just invariant?
Relativistic, it's invariant under Lorentz transformations. In fact, it's not the only one. You could have more complicated invariants, because proper time is not the only one. There are more complicated invariants, but this is the simplest one. Yes, I'm saying that this function should be the same in all inertial frames of reference, and it means that this has to be a relativistic invariant, each of them. And it is. It's a product of for position and for momentum.
Was it important now to go into this other Lorentz transformation? I don't know.
No, you don't. The only we only needed those to justify the presence of those multiple paths. Once you have multiple paths, this is a standard, orthodox relativistic consideration.
There, because you can have multiple paths in normal reference frames that are connected to the normal Lorentz transformation. Why were they important there?
Because I wanted to justify why you do have multiple paths in the first place. In standard classical theory, you have single path, and it was big shock to physicists to discover that objects can move along multiple paths at the same time, right? And Einstein couldn't believe it. This was the thing that he did mind about quantum theory. He didn't care about, Schrödinger equation or anything else. He was puzzled and bothered by the fact that you have unpredictability and you have multiple paths. He thought it's not possible. And it didn't make sense to him. That didn't make sense to him. All the formalism is kind of acceptable, but the most disturbing part is multiple paths and unpredictability. So you need superluminal frames to justify that. And the rest is just relativity.
Assuming the normal kind of reference frame, one path, it's a localized particle, but because you go into this other super Lorentz, then you see that this one path is actually two paths.
So you cannot avoid having multiple paths. That's what I would say. If you allow superluminal observers, it is inevitable that you will have multiple paths, and you have to deal with that. You have to be able to characterize it, and this is the way to characterize it. And you find that the only really description of motion along multiple paths, if it's to be relativistic, involves complex numbers and a complex number attached to each path individually. You have to sum them up and take a modulus square. Or actually any other power as well is fine. Choice of the power may be based on if you want this to be really a probability, you'd have to normalize it, and then probably conditions of normalization will give you what gamma and beta has to be. That's it. I wanted to argue in this work that there is no such thing as a non-relativistic quantum theory. If you adopt this point of view, everything you know about quantum theory is really a relativistic effect. And it's only because there is this bipartition of possible motions to the family that is subluminal and the family that is superluminal. So the speed of light was infinite, which is a possibility. I mean, it's not happening in our universe, but it could be. Then the guess is that there will be no quantum effects. That these quantum effects are only because the speed of light is finite. And also, as probably many of you, I am plagued by emails from crackpots saying about they discovered this proof Einstein and they this and that. And I hate that, and I also hate that this has this flavor, which I admit. But I mean, you be the judge. I struggle to find some sort of inconsistency here, and it looks to me that there is really nothing wrong with superluminal observers and objects. All you get, the price you have to pay, is this element of unpredictability and the quantum superposition, some sort of, that you already know they are true from experiments. So I was unable to find any inconsistency in this description, and to me it makes perfect sense. And also, what is funny is that up to this point, everything that I said could be done by Galileo 400 years ago. I didn't add anything new. I just assumed his principle, and I just kept going with it without any extra assumptions, without removing any of the conclusions. Just keep everything in the theory and see what's the consequence. This is the consequence.
Everything you say on this slide, isn't it independent on the first part of the talk?
Yes, it is. I mean, you have to know that these paths exist. That you have to know that you are forced to consider multiple paths. And this you cannot guess. You could either postulate it, which I don't want to do, and therefore I prefer to infer it from these other considerations. So the multiple paths you get by considering superluminal frames of reference. This you get by using standard special relativistic considerations.
How do you get unbalanced paths like that, like one amplitude?
Good question. I don't. Which suggests that maybe there isn't unbalanced paths. Maybe when you have a beam splitter that is not 50-50, maybe that means you have like 5 paths going this way and 1 path going this way. Maybe it's that.
What is the operational meaning of 5 paths going this way? Like if I measure and get 50-50?
That's my problem. I don't know. This is a very good observation. I'm puzzled by this because I don't get this. And so this is also my problem with this interpretation of quantum theory, where you have what do you call this? This Everest interpretation of many words. Everything's fine until the question, until you ask the question, how do you characterize an imbalanced beam splitter? Because then that means your universe splits into two universes that have different weights, so to say. And this is a problem to I don't know how to characterize it. Yes, but it is true. You get you don't have asymmetries.
Can I go back to the Niels concern? So to me, really, it's not. I think motivation to me could only start with the Bell's theory, not with this one measure. Because surely I can measure in classical physics things that are correlated in the past. I can measure them in space-like separated. I see correlations, and I say, oh, but these correlations are actually A influence B, and then oh, but in other reference frames B influence A. And I would say, well, get it. Nobody influenced anybody. It was locally, it was correlated in the past.
Yes.
So the only way to disprove this is to go through that theory, for which you unfortunately need quantum mechanics to show that you can violate that. So to say, if I would complete this program and say, I go to the Bell's theorem, or I assume phenomenology, I can violate them. So that's why I don't have a non-local invariant model, which doesn't have a preferred reference frame, and so on and so on. But then it seems like a little bit now circular reasoning, a little bit, because the motivation for that comes from the violation Bell inference. If there were no violation Bell inferences, I would say, of course, this is nonsense, because everything is causally local. It's just you measure them simultaneously.
Okay, in fact, this was the beginning. You're right. This was the beginning of the whole idea, and it's not only mine. Also, Arthur had the same kind of. He thought about the same thing many years independent from me, and then discussed it. But the observation is this: you have a quantum theory that does everything it can to annoy special relativity. Like Einstein was furious about quantum theory and wanted to disprove quantum theory with relativity, and he has this EPR experiment. He said, "Oh, look, quantum theory cannot be right because it's non-local, it's against relativity." But then other people showed, no, it's perfectly fine, because there is no information transfer, and when you have these entangled states, you cannot send information because there is unpredictability of the outcomes. You cannot control the source. So what was surprising is that quantum theory does exactly what it can and doesn't go further, as if it knew exactly what it can afford, and as if it exactly knew that there is special relativity and you have to avoid it. So now the question is how these two independent theories know so much about each other. I mean, normally they are considered to be independent theories. As another example, when you have black holes in gravity. Black holes in classical theory would kill information. That would go against second law of thermodynamics, because they suck up information from universe, entropy goes down. And only because of what Bekenstein observed and then Hawking proved, there is no problem, because there is Hawking radiation. So quantum theory comes to save the day. Again, for two independent theories, it's a big coincidence, right? Another observation so it's these two theories kind of fit together very well. And one more thing I would like to say is this: you can rule out superluminal objects from special relativity, and people normally do, and they are fine. They rule out superluminal objects, then they have to postulate on the quantum theory, and they are fine. However, when you consider Schwarzschild's black hole, you have this problem that when you describe the metric in Schwarzschild coordinates, which characterize space-time of the black hole from the point of view of the observers that are sitting in a fixed distance from the singularity, resting observers, then you have a problem when you cross the event horizon, because then time and space is switched. And people don't know how to interpret it. I mean, sometimes they say it's unphysical. I've had many explanations. But it's not unphysical, because when you go to Kruskal coordinates, which characterize freely falling observers, everything is fine in all space-time. So those solutions are physical under the event horizon, and you can interpret them this way, because you say they are still observers that are at rest with respect to singularity, but those observers have to be superluminal to be at rest under the event horizon. And if they are at rest and they are superluminal, they have to change time and space. And that's what happens when in the Schwarzschild metric. So Schwarzschild metric is a perfectly fine description in all space-time, with the one restriction that outside of the black hole, outside of the horizon, there are subluminal observers, and inside of the horizon, there are superluminal observers. And you cannot rule them out. You can rule them out from special relativity, but they go back in general relativity. So I don't think it's a good idea to fight those superluminal solutions. Just treat them seriously, because they will go back anyway and haunt you in general relativity. Yes, this is
also transform the Minkowski metric as we would do in GR by going to these new Lorentz transformations, which are just other coordinate transformations that also change the metric. We wouldn't have any issues with locality or difference.
I mean, in GR people forget about these problems and they just say whatever coordinate system you use is fine. They use light cone coordinates, whatever, and they just do not attach any physicality to those coordinates. That's what they do. So you can use any coordinates you want, like Kruskal coordinates, for example, correspond to a physically freely falling observer, or Schwarzschild coordinates correspond to resting observers, but you can have other coordinates that are not physically attached to any observer. So, I mean, it's fine in GR because people do not pay so much attention to the physical interpretation of those coordinates, because you can use any coordinates you want. I mean, because it's simple. That's why. I mean, yes, in principle, GR you can go to non-linear frames of reference first and infer some facts about GR, and yes, it's just more complicated. But yes, I believe it's principle possible. Yeah.
I think the idea was don't go into quantum theory. Nothing is wrong with quantum theory. You will have an explanation in classical theory, but involve GR. Was this? Yeah.
Oh. Then I didn't understand it. Then. Okay, but I don't see how you would. All I'm saying that your explanation could not be local and deterministic.
Well, if I transform the spacetime, I mean, GR is locally deterministic, right?
Yes, but.
GR can deal with this situation.
But maybe I don't understand then.
But so you're saying, okay, we have these situations, we consider these general coordinate transformations,
yes,
right?
Yes.
And if we want to retain locality, determinism, and the principle of relativity,
You can't.
You can't, right? But I assume your principle of relativity would not transform the metric tensor. It deals with a fixed space-time metric background, right? And you're saying, oh, now the laws with this fixed space-time
Not really. No, not really. It brings the metric tensor is changed. Obviously, maybe you're asking about some invariance like the space-time interval, because the metric is when you apply coordinate transformation to a metric tensor, the tensor changes, right? So.
But if the metric tensor is changed, then I don't run into issues of causality, right? I mean that your second set of Lorentz transformations is just an arbitrary coordinate transformation that will preserve causality, and I just think if I deal with it in a theory, also concerns the metric tensor.
No, but it's in 1 + 1 dimensional spacetime that I discussed here, there is a perfect symmetry between those two families of observers. So you cannot say that these are physical and these are not, because there is you can make a transition from one frame to the one family to the other, and the whole description will be the same. So you cannot say that these transformations are Lorentz transformations that corresponds to motions, and the other ones are not physically valid because they are just some transformation. No, they correspond to an observer that is moving with a constant velocity that is larger than c. Yes, yes, but these are specific enough for me to say that they correspond to a motion with a constant velocity. That I know. So not all transformations, not all coordinate systems correspond to given observers, but these particular ones correspond to observers that move with constant velocities, that I know. So they are quite special. They are not just any transformations. They are special because they have this physical interpretation attached to them.
You can do a detection of this particle between A and M, and also detection of the particle between M and B. So you can have two events that are like measurements between A and M. And when you switch to the other, you will also detect two particles in both. Right? So these two events in this other picture will be two particles detected at the same time slice.
No. No. You can only have one. Because if you detect a photon, you absorb it. You cannot.
No, yeah, can you imagine to have
So it's not a photon, right? Could be a very
could be a bullet
or something, right?
And then I would argue, okay, yeah, I know. People talk about non-destructive measurements, right? This is what you mean, right?
Yeah.
I'm afraid that when you have a non-destructive measurement, it always involves a nonlinear interaction, right? And when you have a nonlinear interaction, that interaction always produces new particles. If you have a Hamiltonian that's nonlinear, you produce new particles. So you can say that when you observe the electron and do not absorb it, what really happens is you absorb the photon, the electron, and then create another one by the nonlinearity. You always have this window of opportunity to interpret it this way. So of course I can absorb the photon and then after gaining the information about it, produce a new one instead of this one. And then it looks like a non-destructive measurement, but it's not the same photon anymore. And therefore, all these non-destructive measurements really involve nonlinearities, and you cannot say that it's always the same electron that you measure. It's kind of some electron, but identity of that electron is, I mean, it's not certain because of the nonlinearity.
Quantum assumptions, to get superposition, because if you would assume that the bullet can be detected without the
yes, exactly. Exactly. So I would run into
correlation that
yes.
you have on particle per path, you need to assume linearity probably.
Yes. So I would run into, you are right, I would run into problems if it was possible to detect a photon without absorbing it. That is true.
Some invasiveness of the measurement
Yes.
or linearity.
Yes. So I am assuming, that would be a problem.
So that here you are still with classical physics, right? I don't see. Classical physics you can really actually, first of all, you could think of a classical photon, right? I mean, you don't perturb it, right? I mean, you just make a really minimal interaction.
Yes. So in a way, I'm assuming that my object here, if I observe it, I always detect it. I always destroy it. Yes. You're right.
The mere fact that you have classical special relativity, that's really the only way you have, in order to start this story, you have, I'm repeating myself, you have to have a violation of balancing point. Because there is no need not to end up in a relativistic classical relativity, special relativity. We have this theory, there is no inconsistency.
Yeah, I know that people. Before we had Bellison inequalities, people argued who is right, who is not, and there was no agreement. I agree. But the reason I'm not so passionate about this is because some people say, so many papers in quantum information start with the statement that entanglement is in the heart of quantum theory, it's the most important part. And even some people derive quantum theory from entanglement and from its properties. I don't like this because I believe that what is fundamental is the superposition, and quantum entanglement is the secondary. Once you have superpositions, entanglement is inevitable. You just consider a superposition of objects that have multiple degrees of freedom.
I want to say that there is, that if you want to derive quantum theory from special relativity, there is one thing that is non-linear, that actually forbids to end up in the classical special relativity. And this one thing is actually probably the most important one.
Maybe you're right. Maybe you're right. Maybe it's my dislike of this claim that entanglement is really fundamental. I mean, I didn't.
I'm not sure you derive this superposition. It's a little bit too there is this kind of assumption, oh no, there is no other photon, this is maybe classical, like...
well, I'm derived, not derived. What I'm saying is that once you allow superluminal transformations, you won't be able to sustain a theory that only has single paths. That's what I'm saying, right?
This could be a classical mixture of left and right. This could be a wave equation.
Yes, but no, not really, because of this detection argument. I mean, this could be two photons, but then you would be able to measure two photons with two detectors, and you can't. So call it what you like, but what is the difference? Well, there's this American saying, like if it quacks, it behaves like a duck, looks like a duck, then it's a duck, right?
You take like the action of some relativistic action for classical one, right? I mean, you apply this special transformation, it will be still invariant, right? Or not?
Sorry, say.
What if you take an action that is classical action that is invariant under relativistic transformation, the standard one, and then you apply this other transformation, the superluminal
Yes.
one. Is it still invariant, or is it sign, or what?
No, it's not invariant. It changes the sign. I mean, if you are talking about the spacetime, the action that is proper time or spacetime interval, it flips the sign because you exchange time and space.
Then you couldn't use it in the other derivation you have put, right? I mean, you're trying to think of relativistic invariance, and you say that this space.
You can, because these changes the sign, and so these change the signs too.
I see.
So it's preserved. I don't know. I already struggled to show this, and I don't even know. I'm not mathematically proficient enough to say what is the body of these objects. I'm sure that it's fine when they are real numbers or complex numbers. I don't know whether you can go beyond. Probably you can. So that would show that there are more general ways of thinking about the possible kind of quantum theories than the one that we know. And you know that if there is this interesting link between the fact that we use complex numbers, the fact that there exist spin 1/2 particles, and the fact that there are 3 dimensions in space. These things are linked, right? This is how you teach the students in quantum theory. Why do you use complex numbers? Because when you have a spin that can be either up or down, you have a base, like this kind of this two-dimensional space. Then if you say, suppose it's z dimension, right? Then if you go to the y dimension, then you have to use a different base that is independent from this one. And this is possible to have a different one that is real. But if you add the 3rd dimension, there are no 3 independent bases that are only consisting of real coefficients. You have to use complex numbers. But if there was a 4th dimension, complex numbers would not be enough. So probably then you would have to use quaternions, right?
You would have 3 y's and x and z. You have 3 y's for 3 imaginary units, I, j, k, and x and z. So you need 5 dimensions.
5 dimensions, yeah. Okay. Oh, yes. Okay, yes, you're right. But there is this interesting link between the number of dimensions and the body of numbers that you use to describe your. So I don't know whether these have to be. Maybe in general, they can be something more than complex numbers. Also, in principle, you don't get Schrödinger equation simply because this is a solution to Schrödinger equation, but also to Dirac equation and Klein-Gordon equation, because plane waves happen to be solutions to all of those equations. So that's why you cannot derive Schrödinger equation, because it's not relativistic, really. So, but this gives you some sort of path integral formalism.
What if you extend here the set of observables, so to say, invariance, not only phi 1 to phi n, if they are okay, but then also for the unbalanced, like you introduce.
Yes, you would have to resign. I mean, you have to abandon this first assumption. Yeah, if you abandon the first assumption, I would. Maybe
you can get it.
It becomes. Probably you can. It becomes more difficult to prove, but I would say that probably you have some arbitrary constants in front of you. Those numbers. That would be my guess. If you abandon the first assumption. But again, since I kind of sympathize with this interpretation of many worlds, and it always puzzles me why you can't describe what it means to have imbalanced superpositions there.
You can simplify as much as you want, but these guys measure this all the time. Unbalanced.
Exactly. But you know what? Maybe there's some sort of the generation of those paths. I don't know. I'm puzzled by this myself. But yes, if you want imbalance, then probably you need to abandon the first assumption, and then probably this is the strongest assumption. Because the Euler theorem I mentioned is the simple theorem that asks what function satisfies the equation that f of x times f of y equals f of x plus y. And Euler has proven that the only function that does it is the exponential function. And this is a generalization of that. Probably if you don't have this balance assumption, this symmetry condition, then yeah, you'd get some amplitudes here.
Like when you write the Lorentz symmetry or the Lorentz transformation, you do it for one space coordinate. Is it straightforward to extend it to 3 dimensions?
Yes. I can show you I should have it somewhere. So if you want to, okay. This is Lorentz transformation, the regular one for 3-dimensional coordinates. And this is the analog of that in the superluminal transform. And here's the problem that I feel I need to tell you about. A serious problem, interpretational problem, because the problem is that once you flip time and space, then this space-time metric becomes this. And the question is, what about the extra dimensions? Because they stay the same. So the question is, what does it mean that time has a negative sign and these other 2 dimensions also have negative sign? And I don't know how to interpret it, but one way to interpret it would be to say that physically, these are the same types of dimensions, so that suggests that there are 3 temporal dimensions and 1 spatial dimension in this case, whatever it means. In fact, it's not so.
But what happened in the case in GR that you mentioned, structure? Like this is the same interpretation of problem?
Yes, it's the same. I mean, it's not the problem of this. It's the same problem that you get in Schwarzschild metric. It's not that this is genuinely attached to what I'm talking about. This is the problem that people have when they talk about Schwarzschild black hole. Exactly this. And physical interpretation of that, to me, is that these guys that are sitting under the horizon are superluminal stationary observers. And they have this that seems to suggest that there is just 3 temporal dimensions and 1 spatial dimension in that, which already brings me to another conclusion, that I told you that these observers are indistinguishable in 1+1 dimensional scenario, but in 3+1 dimensional scenario, they are not indistinguishable anymore. So you would be able to discover that you are superluminal in 3+1 space-time, which only suggests that principle of relativity cannot hold in the kind of strict sense in this real-world scenario. That you cannot discriminate among any of the superluminal observers, you cannot discriminate between any superluminal observers, but those 2 families are distinguishable already. And the kind of weaker version of principle of relativity would be that if you have some sort of description in one frame of reference, for example, involving classical deterministic local theory, then there must be one in the other frame of reference as well. It may be a different physics, slightly different laws of physics there, but the reality you're observing is still the same. That would be the kind of weaker version of the principle. So things get more subtle in the real scenario.
Position, and I boost one with one, and the other with the other.
Yeah, that's what we consider, right? When you have these superposition of different spacetimes. Yeah, there are many interesting questions you can ask.
Okay, thanks a lot. So Andre is here until Friday afternoon, yes, sir?
Yes.
You want to start with him?
If you want to give me hard time for this, just feel free.
Very nice.
Thank you.
A lot of discussion.
So let's talk tomorrow, maybe, yes?
Sorry,
Let's talk tomorrow then.
let's talk to, so tomorrow is also a little bit tricky for me.
Okay.
But I'm certainly, we can talk the day after tomorrow.
Okay.
Tomorrow, a guy is coming to paint my flat, so
Okay. I know. Yeah.
on and off, I have to be there.
just email me whenever if you have time.
If you want to talk with my people, I can arrange this.
Yeah, great. Sure. Okay.
Shall I arrange something?
Yeah, we can.
I write them today an email that connects you with
Okay,
people, and
because
then they talk to
I have many projects that are not involving this, but other stuff.
I'm sure that you might be interested in.
Yeah, yes. I finished on a paper with Fabio and Magda right now on these things. We have found some problems with the with this Bell theorem for superposition of spacetimes. So there are some issues. There are some extra assumptions there that were not clear from the beginning, and
It's not clear, because the surface time, in order to build up the Hilbert space, you need to have a hypersurface of T equal constant, which depends on the metric.
Yeah.
The metric is not.
yeah.
I don't know. I mean, this is one of the issues that I have in mind.
We have found some scheme where you can violate those inequalities without having these superpositions, and then we realize that there's some implicit assumption that you cannot have something, and so we are writing about this right now.
Okay, good. So you can have a definite cause.
You can have some sort of, because the goal of the project was to consider these inequalities, but without gravity. Because if you believe in principle of equivalence, then you should be able to simulate gravity with super accelerations.
Yes.
And we wrote a scheme where it appeared that you can violate those inequalities without clearly being in these superposition
but then the
regime.
local operation